Hey guys, welcome to the H NMR video. Sorry again, I was a little bit sick, so I took a little bit longer to make the videos this time. But let's just get right into it. So in the previous video, we did CNMR, right, which was centered around carbons. So now we're going to do H NMR, so it's all about hydrogens. So this is a little bit different, a little bit more complicated, but if you just take your time, it's not going to be too bad. Okay. So how is H NMR different from CNMR? Well, a lot of it is the same, right? Remember how in CNMR we talked about carbons that are the same and how they don't come up separately. So we did this sort of example. We had this nitrogen right here. So I talked about this example, right? And how we can draw a line of symmetry right down the middle, right? And then we'd look at the unique carbons, right? So what we would consider unique? Well, this carbon right here doesn't really come up anywhere else. This like carbon in the center with the CH2 bound next to it, right? That never really happens anywhere else. Same exact thing for this carbon. But you're going to say, oh, we have this one over here. But remember, we're talking about unique carbons. CNMR doesn't pick up carbons that are the same. It only picks it up one time, which is why, so we're going to get one peak here, a second peak here. We're not going to get a third one there, right? That's a repeat, so we still only have two. And then we have this methyl, right, which you can see is the same as this methyl, which is the same as this methyl, same as this methyl. So we again only get another peak there. So that's 3 total peaks on CNMR. HNMR works the same way, except for one small factor called splitting. All right. So I took this question straight out of your workshop. It asks what will be the splitting pattern of the associated with the signal associated with the indicated hydrogen atoms. All right. So remember, with HNMR, we're always looking at the hydrogen. So what I'm going to do is I'm going to just redraw this so we can see the hydrogens. So the hydrogen that we're talking about, remember how there's 2 hydrogens here, so I'm going to color one red. So again, what we can do is we can draw a line of symmetry, right? It's a line of symmetry down the middle. So remember that in CNMR, we didn't get different signals for carbons that were the same. HNMR works the same way. So let's first look at the 2 H's on that one atom, right? They're bound to that one atom. There are no real ways to tell them apart if I just changed it white. So we're going to get a peak from that hydrogen, right? One of them. Doesn't matter which one. So let's go up to the top. There's 2 hydrogens here. Remember, they're both considered the same. But that's different from this hydrogen, these 2 hydrogens, right? Because if you can see, they're bound to a carbon directly bound to the oxygen. So they're going to be considered different from this hydrogen. So here we go. 1 signal, 2 signals. And now if we look over on our line of symmetry, this group of hydrogens is the same as this group of hydrogens. So we're not getting a separate third signal for those. Same thing as this hydrogen, these 2 hydrogens. We're not getting another signal with these because they're the same as those. Okay? So remember, always draw these lines of symmetry. All right, and so what did they ask us to do? They asked us to find the expected splitting pattern. So this is the difference with HNMR and CNMR that makes HNMR a little bit harder. That some people have a little bit more trouble with it. HNMR, you have to look at the hydrogens next to the hydrogens you're looking at. So let's say I'm looking at the hydrogen in red. We know we're going to get a peak from there, right? So here I'm going to draw like the little the baseline on our HNMR. Okay? And so let's say we're going to get, in CNMR, we would have just gotten a peak like this, right? That's a unique hydrogen. We're going to get one unique peak. And so let's color this one blue so we have a difference. So here's our red peak, here's our blue peak. Don't focus anything about downfield or upfield right now. We'll talk about that later. Right now, we're just going to look at the peaks. So we're going to, in CNMR, we would have gotten 2 peaks like that. HNMR is a little bit different. We have to look at the hydrogens next to it. So we're going to focus on the red hydrogen. Now, we cannot look at this hydrogen, the hydrogens on that carbon for splitting. They're the same thing. HNMR, remember that HNMR hydrogens that are the same don't see each other. So these 2 hydrogens here do not contribute to any splitting. The ones above this red hydrogen do. So the way we talk about splitting, it's called the N+1 rule. Okay? You take the amount of hydrogens on the carbons adjacent to your hydrogen. So that's going to be this carbon right here, color it green. Right? Those are the adjacent carbons, and I'll even color this one. We have to put N as the amount of hydrogens on that carbon. So in this one right here, we have 2. And because I said H and MR won't see each other, so even though we have 2 hydrogens here, because they're the same as these, we're not counting them. So we're still going to just put 2 plus the 1 to help account for the fact that we still have the 1 on the hydrogen we're focusing on equals 3. That means in H and MR, instead of the 1 peak like we would in CNMR, we're going to get a splitting pattern. It's going to look like this. 3 lines clustered right next to each other. Okay, this is going to be called a triplet. So that would have been the answer to this question. Now, just for the sake of it, let's talk about this one right here. If they didn't ask for it, but again, just for practice. So N+1 rule. We're looking at the adjacent hydrogens, 2 of them. So 2 for N plus the 1 equals 3. So the blue line is also going to be split. So we're going to get 2 triplets. So that's how HNMR splitting works. And we're going to get more into it obviously later on. Right? So that's one of the questions. Now we're going to talk about shielding and upfield, downfield, stuff like that. All right, this is again taken right out of your workshop. So they're asking us, this is a CNMR, right? But it's still going to help us with the HNMR. In HNMR, it would have been very, very similar. Okay? So they're asking us to find which peaks are X, Y, and Z for the carbons 1, 2, and 3, right? And again, this is also helps for HNMR as well. So remember that when we talk about shielding, that means we're shielding the nucleus, that proton, right? Not the proton, sorry, the positively charged nucleus with electrons. The more electrons we have on something, we call it shielded, all right? If we're talking about something that's shielded, right, that means we're going to be more to the right on the graph. Deshielded, or less electrons, is to the left. Okay? So let's look at this. The key thing here is that's going to help you figure this out is resonance. And you saw this in your workshop in class. We have this compound, right? What I'm going to do is I'm going to resonate this carbonyl bond up. O minus, positive charge. So look at this. Through resonance, remember this is labeled as carbon 3. We got a positive charge on our carbon, right? We deshielded it. We took electrons off of them. Because we did that, we're going to be so far to the left. We're going to be as far to the left compared to the other carbons, right? Because through resonance, we were able to do this. Full positive charge. So X should be this, right? So X would have been 3. Okay? Now, what about carbon 2 and 1? So if we look, this is carbon 2, and this was carbon 1. Now, what's the difference between 2 and 1? 2 is bound directly to an oxygen, 1 is not. So 2 doesn't have resonance that can help deshield, but it does have induction because oxygen is an electronegative atom. So a lot of the electron density on that carbon is going to be pulled this way. So we're de-shielding again, but through induction. Not as powerful as 3, but still de-shielding. So Y is going to be 2, which means Z is just 1 at this point, right? That's how we would have done that. And so this is going to also be good for, when you're talking about HNMR, because HNMR does also focus on the shielding and de-shielding effects when we're talking about the groups that are attached. Okay, so let's move on. So here's another example. It says in the HNMR spectrum of a ketone, we would expect 3 signals, right? So before we even answer this question, let's go through what that looks like. Here's this ketone. All right. So it says we're going to get 3 signals. Now, when we say signals, that's not taking into account that we have splitting. We have splitting, but when we mean signals, we mean like clusters. So if we have like a triplet, or and then 2 somewhere else, that could be like a doublet, and then like a bunch of other things here, but you can see how they're clustered separately, right? Okay, so that's what we mean by signals. All right, and so it says we would expect 3 signals. Where are those signals coming from? So first thing you want to do is find all the unique hydrogens, right? So here, we have 3 hydrogens here, 2 here, 3 here. Okay? Where are the unique hydrogens? Well, let's look at the methyl on the left. This carbon on the left, the hydrogens on it. So I'm going to just focus on this hydrogen. All 3 hydrogens here are the same as each other. So we can say that among them, there's only 1 unique one. So it's bound to a carbon, bound directly to the carbonyl carbon. Do we have that anywhere else? And let me just color in the carbons to help us. There's 1, 2, 3, 4, right? So it's bound to the carbon, directly bound to the carbonyl carbon. The hydrogens here are bound to a carbon, bound to the carbonyl carbon, but they're not a methyl. They're bound to this other group over here, right? So it's bound to this one. So they're not the same as each other. We do have a methyl over here when we're looking at one of these hydrogens, but it's not directly bound to a carbon. It's bound to the carbonyl carbon because we have this methyl, then it's bound to this other carbon, then the carbonyl carbon. So this one is unique right here, or this group of hydrogens, then this one, and this one. And I'm circling 1 individual hydrogens, but you could, if it helps, think about them as a group. So like, here's 1 set, 2 set, 3 set. Okay? So those are the 3 signals. Now, how would the splitting pattern look? So let's also talk about that. What would the splitting pattern look? So let's look at the hydrogens on the left. So again, I'll underline it. And let's do the n+1 rule. So how many hydrogens are on the carbons adjacent to that hydrogen? Well, remember, we don't look at this hydrogen. We look at that carbon. We look at the adjacent carbon, which is this one. There are no hydrogens there. So it's going to be 0 for n, plus 1 is just 1. So we're going to get 1 peak. It's just going to be a line. It's called a singlet. Now let's look on these hydrogens. So let's underline in blue. So again, remember, we look at the adjacent carbon to the carbon the hydrogen is bound. So if it helps, number this 1 where that hydrogen is bound. That's not the one that you want to look at. You want to look at the one number 2. So in that case, for n+1, the adjacent carbon, which is the one we called number 2, has 3 hydrogens, 3, plus the 1 to account for our hydrogen that we're looking at right here, is 4. So we're going to get a quartet. Okay, 4 lines. And now the last one. So again, n+1. Let's erase some of this to help us make it a little easier. So we're talking about one of those hydrogens. So again here, 1, 2. You want to look at the one labeled as carbon 2. The hydrogen's there. It has 2 hydrogens. It's 2. Plus the 1 to account for ours. It's 3. We're going to get a triplet. Okay? So that's the splitting pattern of our ketone right now. That's not part of the question, but it's good practice to help you with the splitting pattern. So let's look at what they asked us. They said, what would be the expected number of signals in the HNMR of the product of this reaction? Okay, so we're using NABH4 over ETOH. You guys learned this reaction. Remember, it's a reduction of a ketone to an alcohol. So our product is going to look like this. Right? Remember, if you watch the video, the ketone becomes an alcohol. So we're going to get this alcohol right here. Now, how many hydrogens do we have now? Okay? So here's where you need to be careful. We have to find again our unique hydrogens. We've already established that the hydrogens here count for one set. So let's just circle them. So we're still getting one signal there. Same for the hydrogens here. 2. And same for the hydrogens here. 3. Right? You can see that they're still unique. We don't have other carbons like them. Of course, you should always check that because you're based on your reaction, that might change. Okay? Always check. So we still have those 3 signals. Did anything else happen? Do we have any new hydrogens we need to look at? Yes, we do. First of all, there's a very obvious hydrogen on the OH. This one right there. So we don't have another hydrogen on an OH bound exactly like that. So that's a unique hydrogen. That's going to be 4, fourth peak. The not so obvious hydrogen is here. Remember, there were 3 bonds now on that carbon, 2 to other carbons, 1 to an oxygen. But because we had to maintain the octet rule, we had another hydrogen there, right? So that's another unique hydrogen now. So that's 5. So now we're gonna have 5 signals. So our answer is gonna be D for 5. Okay. So that's just a quick intro to HNMR. All right. In the next video, we're gonna actually talk about how to make a structure based on the HNMR they give you. Okay. And these are probably something like this will come up on your test. So be prepared for this. Okay. And I'll see you guys in the next video.